Let's wait for a few minutes. Maybe a late night for some people. So let's see if we get some more people before we start. Okay, so let's get started. So as a recap, last time we basically talked about the power flow equation. Okay, so the power flow equation are the equations that relate the power, the P and Q, to the voltages in the system, right? So remember last time we had PI, the injection as VI, sum of all the nodes connect to VI, Vj, Gij, cosine theta I minus theta J, plus Bij sine theta I minus theta J. So this is the active power flow equation. Then we have a reactive power flow equation. Basically, you switch the role of sine and cosine. So these are the power flow equations. And they basically express the physical laws in the system, right? So they express the Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law in the system. And our goal is always given some information find the rest of the information, right? So this is, for example, given PQ, find V theta. Okay, right. So the goal is, because we have these equations, we can measure, let's say, active and reactive power. Then we solve this equation to figure out the voltage and the angle. Okay? So if you look at the system, right, as a reminder, let's remember first. So let's say there's n buses. And let's say there are n buses. As we said last time, the degrees of freedom, basically the number of independent variables you can set freely. This is 2n minus 1, right? The degrees of freedom means, right, so we have n voltages, n voltage magnitudes, n minus 1 angles, right? So these are together, 2n minus 1 are the degrees of freedom. So they basically, we need this many pieces of information to solve for the rest, right? We need this many pieces. So the idea is really, so we're saying 2n minus 1 values need to be given. given to solve power flow equations. Right? So this is where we stopped last time. Right? So again, the important thing to remember is since the angles, right? For the angles, all we care about is the angle difference. So you can always set one of the angles to be 0, or a global shift in the angle does not impact power flow. Okay, so that's what is n voltage magnitudes for n-1 angles. Okay, so any questions about this before we go on? Right, good. So then the question becomes, right, so we need two n-1 pieces of information. How do I get these two n-1 pieces of information, right? So it turns out there are some buses that there's three types of buses. The way we get these two n+1 pieces of information is by looking at, by sort of separating the type of buses in the system. Okay, so some buses are called PQ buses, some buses are called PV buses, and a special bus is called a slack bus. Okay, and the name comes from the bus information that is given. So let's look at, for example, PQ bus. So you look PQ bus. So what is given? Well, by its name. So the name of the bus, the name, the says basically tell us the P injection, Q injection are given. Okay, so these are given information. V theta are unknown. Okay, so we don't know V and theta. We know P and Q. And the goal is to figure out, determine the value of V and theta once we plug this P and Q into the system equations. Okay. This is what we'll try to do. So PQ buses are basically load buses. Okay. Load buses are PQ buses because if you're load, you don't really, especially if you're sitting after a power electronics conversion stage, voltage is not an issue. All you are doing is drawing constant power, okay, constant P and Q. All right, so, and most load have a power factor associated with it. So it's not that you only draw active power, you also draw reactive power if you're a load. Right, so again, let's go through why it's we think load bus are constant PQ. It's because mostly you're either sitting behind the transformer or you're sitting something like AC-DC converter. Okay, so always there's something that's holding the voltage constant. Okay, so the load operate with the assumption that the voltage is constant and they're changing their power draw. Okay, so these are the PQ loads we have. Okay. So we don't really have that much. So-called the constant impedance loads in the system. Most loads in the system are constant power loads. Right. So the load is PQ, and then PV bus is typically the generator bus. Okay, so what does generator bus do? So PV bus, this says P injection is given. Okay, so I'm a generator. I know how much power I'm injecting into the system. So this is a given piece of information. The voltage magnitude, right? So this is the voltage magnitude is given. So I have an exciter, and my exciter basically try to maintain the voltage at a constant to interface with the transformer to the grid. Okay, so I keep this constant. Then what I don't know is angle is unknown, right? I need to solve for this. Q injected is unknown. Okay, so these are the things I don't know. Right, so and these basically model generators. Okay. Generators are thought of, some generator basically is a constant active power source that can keep its voltage constant at some level. That's how we think about generators. And the thing to remember is, for example, when we look at a PV bus, We say the injection is given, the voltage magnitude is given. It's not like saying the reactive power doesn't matter. Okay, every bus has some reactive upper and lower band. Okay, so reactive power not given doesn't mean it can be an arbitrary number. Right? The reason it's not given is the generator itself doesn't control it, but still has to lie within some range. Okay, so the idea is the generator specifies P and voltage level. Then you solve the equations to figure out Q, and then check whether you're operating in the correct range or not. And the reason you cannot specify 3 numbers at a bus, right? So you may think of a generator, why don't I just tell people P, Q, and V? The reason that you don't have that many degrees of freedom. You run out of degrees of freedom. But basically, you cannot specify 3 numbers at a bus because you cannot independently specify 3 numbers at a bus, right? So you don't have that many independent variables to choose from. Okay, so you normally pick 2 independent variables, right? You pick 2 of them. So in the load, we pick P and Q. In generators, we pick P and V. Okay, so that's the way we decide which ones to pick. So this comes to be an interesting question is, remember we have 2n minus 1, right, degrees of freedom. Okay, we have 2n minus 1 degrees of freedom. But the problem is, right, the problem is, so I have 2 basically PQ bus or PV bus. But for each PQ and PV bus, I give you 2 pieces of information, 2 numbers I can specify. So if you count it this way, it seems I'm giving you 2n numbers, right? So I'm giving you 1 additional degree of freedom. So there are issues there, right? So what do? Right? We counted, we said there's 2n minus 1 numbers we can pick independently. But if you go through each bus and you say, okay, your PQ bus, your PV bus, and so on, it seems you're given 2n pieces of information. So how do we solve this? How do we deal with this issue? Right, so assuming basically we don't have enough unknowns. Seems like we have too many equations compared to the number of unknowns we have. Then that creates a problem of not being able to solve the equations. Right? There may not be a solution to the equations. Okay, and if you think about this issue, right? So a lot of this issue comes down to from the fact that we cannot specify all the powers at all the buses. Okay, so we cannot say that, right? Because if you think about it, if you sum up S generation, so this is the total generation or the system level total generation I generate. This is equal to the S load. Oh, sorry, this is S load. This total load, so the system load, plus S loss, right? Plus the loss in the system, right? So this has to match, right? This power balance equation has to hold. The generated power is the consumed power plus the loss in the system. But the issue is, this depends on V and theta, right? The loss depends on the current flow, and the current depends on V and theta. So basically, we cannot choose the total generation and the total load at the same time. So we cannot make this choice, right? So we must have some slack. Right? The idea is because I need to balance this, I need some slack. So if you can look at this in a 2-bus setting, for example, let's say I have 2 bus. Let's say this is the load. Let's say the generation. If I say this is, let's say PL, QL. So let's say I have a line, some Y impedance, sorry, some Y emittance on the line. I have PL and QL here. For this generator, what information should I provide, or what constraint or what value should I give for the generator bus? Can I give something like PG? can specify PG, right? So you count this thing, there's 2n minus 1 as 3 degrees of freedom. Okay, degrees of freedom, right? So I need to give 3 numbers to solve all the equations. So for the load, I give you P and Q. Then for the generator, what should I give? Should I give the active power of the generator? Should I give the reactive power? What should I give the voltage?
I'd guess the voltage.
Just the voltage, right? Because I cannot give you PG, right? PG cannot be independent of PL, right? Because the load will determine the current, and then the current determines the loss. The load plus loss is the generation. So if you arbitrarily assign a power generation to the generator bus, then the equation is probably infeasible. There's no solution to it. Okay? So it turns out the generator needs to psi V. Okay, so V is the value, the magnitude, right? The magnitude of the voltage it can set. Okay, so once you set the magnitude of the voltage, you have 3 numbers, right? And those turns out to be the 3 correct pieces of information to solve the power flow equation. Okay, so most of our buses are PQ or PV, except one special bus, okay, because we run out of degrees of freedom in the system equations. Right, so we can look at a similar situation. Let's say I have 3 bus network. Okay, so let's have 3. This can be PQ, this can be PV, right? It's possible. But then turns out this can just be, I can only specify one piece of information, which is the voltage. Okay. So this is what happens for a system of, right? For a power system. As you look through all the buses, turns out, right, you can assign 2 and minus 1 numbers, and you always left over with one bus that we don't specify P or Q, that we only pick V. Okay, we only pick voltage magnitude, and this is called a slack bus. Okay, so this is called a slack bus. Okay. So first of all, any questions with this example? Okay, so equation counting turns out to be important, right? When you write your own programs, most times the bugs come from the fact that the number of unknowns doesn't equal the number of equations. Okay, so that's the first thing you want to make sure is you want to count. This is consistent with each other. So once you make this count, what you can do is, so we cover this, and this is called a slack bus. Slack bus basically just means that a bus where the injection power is not specified, as leave as a function of all the other variables. Okay? This way, you don't run into infeasibility, or you can prevent yourself from running into infeasibility. Okay, so then what this does is basically this can be whatever the system needs it to be to have a feasible system. Then what happens is you can wait for a convenience. We also set the angle to be 0. Okay, as a slack bus, since we can't always set one angle to be 0, it just turns out for the slack bus, we'll set the angle to be 0. Okay, we'll set the angle to be 0. And so then the slack bus is basically a bus where you pick the voltage, set the angle to be 0, and PQ is whatever it works, right? So it's whatever it works out to be. Okay. So that's why we almost always choose a generator bus to be the slack bus. It's because once you compute, you solve the rest of the network. Okay, you solve the rest of the network. The slack bus, can provide P and Q to balance the system and to maintain the system to be feasible. So any questions about this? Okay, so in practice, in real life, right, there's no slack bus, right? So when you operate a real system, you put on generators, you put on loads, the power flow is whatever it is. Right, so slack bus in some sense is a more artificial construct. Is a more artificial construct of the way we think and solve equations in a power system. And the reason we use slack bus, is again that angles are relatives, right? So we need to set one angle 0. We may just well set angle to be 0 and to leave the power injection not given, so we can make the system always feasible. So in practice, does the choice of slack bus matter? Does the solution in the system change if I change which bus I pick up? I designate basically as a slack bus. Right, so turns out the choice of slack bus changes a little bit. Okay, so change the solution a little bit. So this choice of slack changes the solution slightly most of the time. Most of the time, it changes, it doesn't change the solution by a whole lot. But because you're basically fixing the voltage of that bus as a variable, so depending on which bus's voltage you fix to be 1, right, to be at the fixed voltage magnitude value. So this changes change the solution slightly, not terribly large. There are different ways to do slack buses. You can distribute the slack, for example, if you want. But really sort of, you can distribute the slack, but it doesn't make too much of a difference. So in practice, every system has a well-known slack bus. So every system just picks a bus to say, okay, you're slack bus. Normally it's a big generator. That takes snap bus. Okay, so so let's summary. If you count the equations, you have 2n equations, 2n minus 1 degrees of freedom. And you solve for the rest of the unknowns. Solve for the unknowns, basically, using the 2n numbers you picked. So we have PQ, PV, and the slack bus. Okay, so this is the equation counting, basically the counting of the equations. So for example, let's look at a 3-bus example. Let's look at 3-bus example, look at how all the equations work out. Okay. So we're going to write down the full power flow equation for this 3-bus example. Okay, so for this bus, if we write the Y matrix, so let's say, so here, these are the impedance. Okay, so normally, if you build a system, you can measure the line impedance. So the first step to building the Y bus matrix is to convert this to the admittance. So we convert these impedance to the admittance. We have minus J10, minus J4, minus J5, right? So here we're going to assume all the lines are basically susceptance, are basically sort of purely lossless lines. Okay, and then what we do is we build a Y matrix. This turns out to be a completely imaginary Y matrix, which is fine. If it's completely imaginary, that's a perfectly okay Y matrix. 10 minus 14, 4, 5, 4, minus 9. Okay, so this is our Y bus matrix. Then let's write down the power flow equations. Let's write down the power flow equations. Right, so if you write down the power flow equations, Okay, so let's do this once, right? So again, we have an active power balance and a reactive power balance. Okay, so if you plug everything into these two equations, right, what you get is P1 equals to minus 15 V1 squared sine theta this is 10 V1 V2 sine theta 1 minus theta 2 plus 5 V1 V3 sine theta 1 minus theta 3 Q1 15 V1 squared minus 10 V1 V2 cosine theta 1 minus theta 2 minus 5 V1 V3 sine. Cosine. Right, and so on and so forth. So you basically get a bunch of equations like this. Okay, you get a bunch of equations like this. And this gives us a system of, this is a system of nonlinear equations. Okay, this is a system of nonlinear equations we have. And we need to solve the system. Okay.
Professor?
Yeah, go ahead.
How you get the equation P1 to Q1 from all the like 10, 5, 15, and
Oh, okay, so let's plug in all the numbers then before we do the, okay, so let's plug the numbers and get P1 and Q1. Okay. To read it. So first recognize that there's no G, right? For this system, G is all 0. Okay, so G, this is entirely 0. So I don't need to worry any terms with a G. So let's look at P1. Okay, let's look at P1. So I'm summing, right? I goes to 1 to n. So here I'm summing 1, 2, 3. Okay, so what the first term is V1 squared, right? V1 times B11. Okay, so what's B11? B11 as you go read off this term. This is right. So the B matrix. So the B matrix itself is minus 15, 10, 5, 10 minus 14, 4, 5, 4 minus 9. Okay, so B11 is minus 15, right? You read it off as minus 15. Sine theta 1 minus theta 1, right? So if you read this equation, this will eventually cancel out, but if we just follow the equation, we can write it out. Theta 1 plus minus theta 1 plus, now it's V1, V2, right? The next term in the sum. Look at B12, this is 10. Sine theta 1 minus theta 2. Then V1, V3 times 5 times sine theta 1 minus theta 3. Okay, so these are the equations we have. Okay, so then Q1, we can do the same thing, right? So we have V1 squared, read out minus 15 here. Right, so we have minus 15, so plus 15. Cosine of theta 1 minus theta 1, that's fine. So here again, as a reminder, theta ki is theta k minus theta I. So it's a difference of the angles. Okay, theta k minus theta I. So we have this kind of equation plus, here, this case is minus, right? So you read off this 10 term, V1, V2 times 10 times cosine of theta 1 minus theta 2. Okay, and then this is minus V1, V3 times 5 times cosine theta 1 minus theta 3. Okay. Any questions about this?
Why is the second term in the Q1 equation negative, the negative V1, 2, V1, V2?
Oh, okay, so because you have a negative sign here, right?
Oh, that's right. Okay, yeah.
Right, so that's a negative sign. So you have a negative sign, then it's negative 10. For the first term, you have a negative, but you have a negative 15. So
Right.
okay. Yeah.
Thank you.
Yeah, so these are the equations we have, right? So just basically you have the two basic equations, and now just plugging all these numbers. Right? And so the nice thing is you don't need to write all the terms, you know. Most times you'll be having angle subtracting itself. So times this angles are 0, this is 1. So in the shorthand form, for example, we just have P1 as 10 V1 V2 sine theta 1 minus theta 1 2 plus 5 V1 V3 sine theta 1 3. Q1 as square V2 cosine theta 1 2 minus 5 V1 V3 cosine theta 1 3. And so on. Okay, so this is the set of equations we have. Okay, so those are the equations, but this is still a linear set of equations because it includes the multiplication of voltages and has a sine and cosine terms inside of it. Right, so solving them, you know, may or may not be easy, but the idea is we first write out this set of equations and think about how we go about and solve them. Okay. Any more questions about this equations? Okay, so once you write out all these equations, then let's look at the different type of buses, right? So let's say here bus 1, we said it's a slack bus. Okay, we said a slack bus. Angle 0, V is 1. And almost always bus 1 or bus 0 is a slack bus. That's a numbering convention. Okay, we just number slack bus being either bus 1 or bus 0. So here, let's say I have a load. This is a PQ bus. And bus 3 is a generator bus, is a PV bus. This is a PV bus. Right? So these are the 3 types of bus we have. And let's see what the equations become once we specify the types of buses. Right? Buses. So the terminology is what you tend to hear, sometimes see, and in the book you see this, as you see a terminology called implicit equations. Okay, let's spell this out. Implicit equations basically means that the injection is given. Okay, so if the injection is given, it's called implicit equation because the idea is, right, so once implicit equation means I fix the injection, but I don't know V and theta. Okay, so V and theta is determined implicitly from the injections. Okay, so that's what you see this term that means, right? So here the implicit equation where injections are given as P3, P2, and Q2, right? These are the places where the power injections are given to us. So we go and write out all these equations. We have P2 as 10 V1, V2 sine theta 2, 1 plus 4 V2, V3 sine theta 2, 3. We have P3 is also given minus, sorry, yeah, P2, let's write Q2 first. Q2 minus 10 V1, V2 cosine theta 2, 1 minus 14 V2 squared minus 4 V2, V3 cosine theta 2, 3. Okay, and the last one we have is a P3 from the PV bus. So we have P3 equals to 5 v1 v3 sine theta 3 1 plus 4 v2 v3 sine theta 3 2. Okay, so these are the implicit equations. Again, the left hand side is given, the right hand side we don't know. Okay, so
Professor?
it's given. That's sort of, we don't know v and theta on the right hand side. Any questions about this?
Yes, when you say the theta 2 1, what means the theta 2 1 is theta 2 minus theta 1?
Yeah, theta 2 minus theta 1. Yeah. Right. Yeah, so it's too lazy to write out all the subtractions. And so you see something like theta ik is always theta I minus theta k.
Why do you do theta 2 minus theta 1 there, but on the next one you do theta 2 minus theta 3?
Oh, so it's always your angle minus your neighbor's angle, right? So these two terms, one comes from this branch, one comes from this branch. Right? So theta 2 minus theta 1 accounts for the power flow out of bus 2 to bus 1. Theta 2 minus theta 3 accounts for the power flow out of 2 to bus 3. Right? So these are the branches. So if you look at the summation equation, for example, from bus k, we're fixing k, right? So we're fixing the first index, and then we're changing the second index on the angles. Meaning we're looking at a bus, the power flow out of this bus to the other buses. Okay. Yeah, so this is notation, right? So we always think about the power flowing out of the bus, even though if it's a load bus, right? So theta 2 1 is probably negative because it's consuming some power. But anyways, that's a equation we'll write it this way, okay, for consistency. Good. Any other questions with this?
I guess I have a question. Maybe I'm missing something for P1.
Mhm.
When the last term is sine of theta 2 3. But
So
since
this is
it's
P2.
oh, okay.
Yeah, so
Okay.
P1 is not given, right? So P1 we don't specify the number. P1 is computed from other things.
Okay, makes sense.
Yeah, P1 is computed from other things. Okay, so so basically the equation that computes P1 is called explicit equation. Okay, called explicit equation. So if you look at P1, this is 10 V1 V2 sine theta 1 2 plus 5 V1 V3 sine theta 1 3. So P1 is not given, so we don't know the left-hand side of this equation, right? So these equations are computed after we figure out what V theta are. Okay, so these are not part of our solution process. Okay, so Q1 is 1 squared minus 10 V1 V2 cosine 2 minus 5 V1 V3 cosine theta 1 3. Q3 is minus 5 V1 V3 cosine 3 cosine theta 2 9 V3. Okay, so these are explicit equations. So this means that they don't enter into the picture when we're solving the power flow equation, because the left-hand side is not given to us. Okay, so there's nothing to solve for us here. Okay, so then when we solve the equations, what do we do? Right, when we solve the equations, the system of equations we solve is the following. Right, so we know these are the implicit equations where the powers are given. We also know, if you look at this, right, we know the voltages at 3. We know the voltage at bus 3 and bus 1. Okay, so what we know is we have V1 equals to 1, V3 equals to 1. Okay, so altogether, this gives us a system of equations. And normally we add a dummy variable. So not a dummy variable, but we'll choose angle 1 to be 1. So V1 equals 1, V3 equals 1, theta 1 equals to 0. Okay. So this we have, this is our equations we have, right? So we have 6 equations, 6 unknowns, right? Some of these equations are simple. For example, v1 equals to 1, v3 equals to 1, theta 1 equals to 0. Some of these equations involve the power flow, right? Involves power flow. But altogether, you solve them all together, this determines v1, theta 1, v2, theta 2, v3, theta 3. Okay, so this is the goal we want. We collect these into a set of nonlinear equations. Then we solve these nonlinear equations to determine the v and theta numbers. Determine v and theta numbers. Okay, and once we have the v and theta numbers, then we can plug them into the explicit equations to compute P1, Q1, and Q3. Right? So P1, Q1, Q3 are computed after we solve for the angle and the voltage. Okay, solve for angle and voltage after we do that. Okay, any questions about this? Right, so if you look at this for a large system, right, you look at this for a large system, basically still the system of equations is quite sparse, right? Because we have this GIK, GKI and BKI terms. These are only non-zero when the two buses are connected to each other. And for a large system, they're often non-zero. For large, sorry, they're often zero. For a large system, they're, most times these are zero. So you get quite a sparse set of equations. So it's quite sparse. And but the problem is, even though it's sparse, it's nonlinear. Okay, so it's not super great for us because it has multiplications and sines and cosines, all different things. You directly input this into a computer, it probably won't solve it for you. Okay, so when you solve nonlinear equations, right? So the saving grace a lot of times in practice is these nonlinear equations again are sparse. And second is a very particular set of nonlinear equations, right? So we have a lot of experience in solving them. But before we go into the details of solving a system of nonlinear equations, any questions about this? Any questions about the formulation of the problem? We were going to solve it. Okay, so if not, then let's break now. I guess this is a natural place to take a break. So let's break now. We'll come back at 10:25. We'll look at how to solve nonlinear system equations. It's actually not a very difficult, sort of very intuitive way of doing it, but I'll look at how to solve it. Okay, so let's break until 10:25.
Professor?
Yeah.
Can I see your code 3?
Code 3?
Can I see your Q3?
Oh, Q3, okay. This one?
No, this one go up. Yeah,
This
yes.
one? Okay.
So since we know the P2, Q2, Q3, and V1, V3, and the state 1 equal to 0, and we got a 6th equation.
We have 6, yeah, we have 6 equations.
And this is the 3 bus, 2 times 3 minus 1, the 5.
So the minus 1 comes from the fact that theta 1 is 0, right? Right, so we can set theta 1 to be 0. But so let's say, if I change theta 1, if I don't set it to be 0, let's say I set it to be any arbitrary number. Does the solution change?
Oh, yeah.
Right, the solution doesn't change because I can change all the angles by the same amount. So setting theta 1 equal to 0 is actually a sort of almost a dummy variable. You can think of theta 1 equals 0, right? But so we just set it to be 0 as a convention. Really wouldn't change anything else about the equations. We solve them.
So from this 6 equation, what we want to get, what solution we want to get? Like the
We want to solve for the V1, theta 1, V2,
Mhm.
theta 2, V3, theta 3.
Okay. And bus 2 is the PQ bus because it's giving the apparent current, apparent power.
Yeah, it's a load. Yeah, so given both P and Q.
Mm. Thank you.
Okay, thanks. All right, so let's get back. So remember the equations we had as a system of nonlinear equations. Okay, so before we solve a system of nonlinear equations, let's try to solve a scalar nonlinear equation. Okay, let's try to solve a scalar equation. So for a scalar equation, almost always we'll write this equation like in terms of fx equal to 0. Okay, so we'll almost always just write it this way. Now, can you solve fx equals 0? Find the x such that fx equals 0. Okay. And for example, if this curve is f of x, then the point we want is x star. X star solve f of x. So the idea with nonlinear equations is normally we don't have a closed form formula. Okay, very rarely do we have a closed form formula, right? So by closed form formula, we mean that you know, a formula that can be evaluated using elementary functions. We typically don't have that. Okay? There's no easy way to get that. And also, when you solve a nonlinear equation, there's nothing that guarantees there is a solution or there is a unique solution. Okay, so unlike the system of linear equations, we have a very well-developed theory of the uniqueness and the existence of solutions. For nonlinear equations, we don't. Okay, we just, if you give an equation like fx equals 0, you just try to solve try to solve it the best you can. Okay, try to solve it the best you can, right? So all the algorithm basically I'll present here is to say that something we can try, but there's no guarantee. There's no guarantee it will work. Okay, so our algorithm, right? So if we look at scalar function, something like fx equals 0. So we don't know whether x star exists, right? So whether there exists a fx star such that it equals 0, this is something we don't know. By looking at the equation, sometimes it's very difficult to know whether we have existence of solutions. That's what we don't know. We don't know the uniqueness of solutions. Okay. So maybe there is fx1 star, fx2 star that both equal to 0, but they are not equal. Okay. Maybe this is the case, right? And again, we won't know this by looking at the function. It's very hard to determine which of these will happen. Okay. So we solve this kind of equations. Basically, the method will be to essentially try and see. Okay, so if you try a method, if you find the solution, you have to look at the solution and use your judgment on whether it's a good solution, or you try a method, it doesn't converge, whether there's no solution, things like this. Okay, so there's really a clear cut and dry answer about this. Okay, so that's something to keep in mind when solving nonlinear equation when you're solving even a scalar nonlinear equation. So for a system, it's even more complicated. And so when we talk about a system of equations, right? So system of equations, what we'll write is f of x equal to 0. We'll still write this, but we're going to think of x as in some real, right? X is in some vector in a real number, and then fx is in Rm. Okay, so when we have by a system of equations, we mean we're mapping. So the map is, let's say n by m. So let's say n by n for simplicity. So the f maps Rn to Rn. Okay, so we have a system we mean that all the equations are 0 at the same time. So that's the solution condition we have. So before solving a system of equations, let's look at what happens to a scalar equation. Okay, so the idea is always to use the linear equations as an approximation. Okay, as an approximation. The idea is the only thing we know is to solve linear equations. Okay, so assume you have a function call that will solve linear equations for you. And the algorithm design, the goal is to build the algorithm using this sort of basic function call. And this is quite common in algorithm design, as you figure out what you can do and what you know how to do easily. But everything else is built out, on top of this elementary steps, right? And basically, if you take an iterative step every time you, call a linear function solver, hopefully you eventually solve the nonlinear equation. Okay, and the idea is, quite intuitive. So if you look at a linear approximation, okay, right? So let's say I have a nonlinear equation, right? So the first step is, let's say I guess, okay, x0. Right? Let's say I start at some x0, I guess the value of this x0. And obviously, f of x0 is not equal to 0, right? There's some value that doesn't cross the x-axis here. But even this guess helped me give me some information. Okay, this guess gave me some information. Because what I can do is, I can basically, if I guess at this point, what I do is I figure out a linear approximation of the function. I figure out the linear approximation of the function at this point. Okay? So I use a tangent to approximate my function I want to solve. And then I draw a tangent. I draw a tangent. Then instead of asking, okay, we can ask, when does the linear approximation equal to 0? Okay, we can ask this question. Okay, right? So we cannot solve the nonlinear equation. We'll guess on point. And most time you won't be very lucky. So you don't guess immediately, you don't guess correctly. But that's okay, right? Because what you can do is you can approximate your function. You can approximate your function using the tangent and ask, when does the tangent cross 0? Okay. I ask, when does the tangent cross 0? So to get the slope of the tangent, we have to take the derivative of the function. So the idea is we take the derivative of the function, we get a linear approximation, and we look at if we can solve this linear approximation or not. Okay. Okay, so we have this. Once we have this linear approximation, what we can do is we can ask, when does our linear approximation crosses 0? Okay.
Just
So
a
we
quick
do
question.
this. Yeah, go ahead.
So the function f of x is unknown, correct?
Fx is known, right?
Oh, it's known? Okay.
Yeah, if it's unknown, then what hope do we have for solving this, right? So for the powerful equation, you know the function, right? Yeah, so go back to this. We know all these functions, right? So these functions are explicit; they're given to us. We just don't know what v and theta make them, equal to 0, or we don't know what v and theta solves this equation, but we do know f. So f is explicitly no. F is we don't know f. There's no question to solve. Right? So we know f, but we don't know when f equals to 0. Okay. So this looks trivial for a scalar function because you can always just graph it and look at the point when it's equal to 0. But let's think of a sort of a more general methodology of how to solve it when it equals to 0. Okay. So if you look at the linear approximation, what you have is basically, so forget about f of x. Now think of this tangent line That's your linear approximation. Okay, this tangent line is now your linear approximation of f of x. And this goes through the point f0. What's my label? Okay, f0. x0 has slope f prime of x0. Okay, so it's a line. A line is defined by a point and slope, right? So it goes through f0 and has slope f prime, the derivative of f evaluated x0. Okay, so let's call this point x1. Okay, let's call this point x1. So can we figure out the value of x1? X1 is a solution to a linear equation. Right, so how do we solve for x1? Right, so we get, if you write this, if you write this equation out, basically what we get is, what we have is f of x0 is f prime of x0 multiplied by x0 minus x1. Right, so this is our basic equation of a line. Okay, so use this equation as a line, then we have as x1 equals to minus fx0 f prime x0 plus x0. Okay, so this is, so we can find, so for a linear equation, we can easily solve for x1. Right, we may not be able to do this. We may not be able to do this for the nonlinear equation, but for a linear one, this is fine. Okay, that thing works. Okay, then what you do is, right, so this is your x1. So this just repeats the calculation. The idea is to repeatedly linearize this. Okay, so let's say this is your first point at x0. You drop a tangent, you get to x1. Then you evaluate the functional value f of x1. It's not 0, but it's getting close. Right? It's not 0, but it's getting quite close. Okay. Then you drop a tangent, for example. Then you evaluate the point fx2. It's not 0 yet, but it's getting quite close. And hopefully this process will converge to the point when the function when the actual to the sort of the true 0 of the function. Okay? So this is the idea of success of basically linear approximation. Right? So for each linear approximation, you're basically getting closer and closer to the true solution. And hopefully after some steps, you'll be close enough to the true solution. Right, so this is the idea clear here. So the intuition is basically just approximate the function. So the only thing we know is how to solve a linear equation. So let's keep approximating this function.
So are you just kind of educated guessing your first point x0?
Yeah, so first point, you typically have some random guess.
Okay.
Yeah. So actually no. So let's maybe look at that. So whether this thing converges or not, depending on your first guess, right? Because once you do the first guess, everything else is determined. Once you guess the first thing, then you have a sequence. Turns out for power system equations, most times your random guess, right? You need to guess a initial v and theta. Your random guess will be v equals to 1, theta equals to 0. That's so-called a flat start. So that will be your random guess. Again, 95% of the time, that random guess works. 5% it doesn't work. And really, that 5% causes a lot of headaches for us. So the random guess matters. Normally, you set it to be a flat start for a power system. But then if it doesn't work, it's not so clear what we do. Right? That's one difficulty with this for nonlinear equations. It's dependent this first guess. And sometimes you need to get lucky. Sometimes you develop a lot of intuition about the system to know how you guess. That's good. Right. So, but once the first guess is fixed, then we can solve the system equations. Okay. So turns out the theory, so we can sort of make this more formal, this sort of successive linearization more formal. The idea is basically to think of a Taylor series extension, right? So if you think of a function, fx, a Taylor series, assuming the Taylor series, this function has a Taylor series. So f of 0 plus f prime x0 x1 x minus x0 plus 1/2 f double prime x minus x0 squared plus da da da. Okay. Right, this is our Taylor series extension. We're going to ignore the higher order terms. Okay, we're going to ignore the higher order. Okay, we're going to ignore the quadratic terms because those are, not good terms. Those are, hard to work with. So we say that, so we solve, right? Instead of solving fx equals 0, let's solve the simpler equation, the Taylor series expansion equals 0. Let's solve this. Okay, so this is a linear solution. This is a linear solution. So we get x equal to x0 minus zero, right? So this is the first term. But because we did this approximation, of course, this solution is not exact. So we need the iterative, right? We need to do the iteration. And we get this sort of iteration to solve the so we keep iterating on this equation, and hopefully this thing will converge. Right? And the hope is, right? So if xk is such that fxk equals to 0, then xk plus 1 equals to xk. Right? At least this sanity check works out. So if you happen to find a point that solves the nonlinear equation, then that's fine. Then your update stops. And then if you're basically, if you're getting close, the f of xk is a small number, right? Then so you're sort of keep approaching the right solution. Keep approaching the right solution. Any question with this? With this theory? Okay, so then we can keep, right? So this is sort of the formal, this is a typed out example. Then the example is, right? So this example basically shows us a case that, sometimes it works, but you're not sure which solutions you get, right? So let's say we take this, quadratic. This is quadratic. So quadratic has two solutions, right? This quadratic has two solutions. And let's see, if we start, let's say we do this example, what we get. Let's see what happens. Let's say we start at x0 equals 6. We do some iterations. Let's see what we recover from this. Okay. So here f(x) equals to x squared minus 5x plus 4. x0 is 6. Okay. Then we need to compute the derivative of the function. Right? To compute this derivative, what's the derivative of a quadratic for this one? Right, so that's 2x minus 5. So you'll be computing quite a number of derivatives, right? So time to brush up on derivatives if you haven't seen it. Mostly derivative of sine and cosine. Okay, so remember the power flow equations has a lot of sine and cosine in it. We'll be taking derivatives of those, and you'll be seeing a whole lot of sine and cosines also, right? So it's good time to brush up taking derivative of sinusoidal functions. Okay, so these are because for Newton Raphson, basically you require two things. One, I can evaluate the function, which is almost always trivial. I know the function I want to solve, I can evaluate it. Two, I need to compute the gradient or the derivative. right? And sometimes that gets messy. But for this example, it's quite simple. Right? So if we do our iteration, right? Let's do our iteration. So we have xk plus 1 equals to xk minus f of xk divided by I prime xk. Okay? So we can let's see we do this. Let's see what happens. Okay? See what happens. So we do one step, then x1 equals to 6 minus 6 squared minus 5 times 6 plus 4, 2 times 6 minus 5. You plug in all the numbers, you get 4.57. Okay, you got 4.7. So what happens is basically you are going to successively sort of march towards this right-hand point. Okay, you're going to march towards the right-hand solution of this thing. Right, so you can do this. You can repeat the step. Next time you get x2. Okay, just repeating the exact same step. Right, we're computing. Right, so we're going to repeat the same step using our equations. And then we keep going. Then basically we got a table. Okay, we got a table. Eventually we get to 4, which is the correct solution. All right, so eventually we bounce. We'll keep bouncing and we get to the solution 4. So this is one example of using interruption.
So
Okay, yeah, go ahead.
So eventually we want xk plus 1 equal to the 0?
No. Xk plus 1 is a solution, right?
Okay.
So what you have is xk plus 1 equals to xk minus f of xk, I prime of xk, right? This is our update equation.
Yes.
What do we want? We want this to be 0, right? So we want f of k plus f of k to be, close to 0. So if this is close to 0, I don't update this equation anymore. I stop updating the equation. So for example, if you plug 4 into this update, it would not update. Okay, would not update. Okay, so this is basically the idea is very simple, right? The idea is very simple. You do the Taylor expansion, you forget the higher order terms, you just keep the constant and linear term, solve a linear system equations, repeat the process. Okay, just keep going. Right? So it's a fairly simple process. If you need to code it up, it's actually a very simple code to write. It's quite simple because it has nothing like step size, nothing like that. You pick one initial point, and then everything else is just determined by the function itself. Right? Any other questions about this? Right, so we'll get the right-hand solution, right? So so obviously there's issues with this, right? Things can go wrong here. So what are the possible things that can go wrong for this method? There's no guarantee this thing will always work out. Sometimes things, even non-obvious things goes wrong.
If you don't make a good educated guess for x0.
Right, so things go wrong basically if you don't make a good guess for x equal to 0, right? So that's right. So for example, here 6 is a reasonable guess, right? Because it's not too far away from 4. It's to the right-hand side of 4, so we imagine it will converge to 4 and so on. But let's say you guess, right? So you can guess at 8. 8 also works. You eventually get to 4, right? But then if you guess to the right-hand side of the right-hand solution, you get to 4. But then things become less clear. You guess something like 0.275 or x0 equal to 0. Right? So things are not so clear once you make these guesses. Okay, once you make these guesses. So, right, so you make these guesses. The problem with this is you have multiple solutions. So it's not obvious which solution correspond to which x0. It's not obvious which one you will get. Okay, so in practice, you may always have a preferable solution. But there may be sort of practical reasons why you like one solution better than the others, but you don't know. It's like sometimes it's very hard to know. Sometimes it's very hard to know which you get. Okay. And for example, if you look at multiple guesses, you end up sort of all over the place. And sometimes you get to 4, sometimes you get to 1, sometimes there are cycles around in the system. So it's quite not obvious which you get. Okay. And it's not always the case that if you start close, it's not always that if you start close to the desired solution, you will get to the desired solution. For example, this is one example, right? So maybe I want this desired solution. Okay, so let's say I want this desired solution. Okay? There's reasons why I think that's a solution that makes physical sense. Okay? So let's say my guess is I will guess, let's say I guess fairly close to the desired solution. Right? You imagine if I'm not too far away, maybe I will converge to the desired solution. For this kind of problem, not always, not always. For example, here, when you guess close to the desired solution, you actually bounce all the way around and come to the other solution. Right? Just the way this Newton-Raphson works out. Right? Just the way Newton-Raphson works out. Okay? There's no guarantee. If you start close to one solution, you end at that solution. And there's no, right? And this creates a lot of times in power systems. Because you think of the power flow, let's say we're solving the power flow equation, we need some initial guess, right? So one sort of obvious natural initial guess is a flat start, as all the voltages are 1, all the angles are 0. That's sort of the obvious guess. But can you think of some other obvious guesses when you solve the power flow equations? Like what are some reasonable ways to guess initial solutions? Right, any ideas? Let's say I have a power system that's operating, that's going along. And somebody says, okay, you have to keep solving this power flow equations, right? And then you ask, okay, so I need some initial guess when I solve the power flow equation. So one very reasonable way to do it is to take the last solution you got and use that as the initial solution for the next problem. So what always happens in power flow is this, right? The load will change, let's say hour to hour. Okay, a load changes hour to hour. So let's say I'm solving the load, I'm solving power flow for 11 a.m. Okay. A reasonable thing is to say, okay, let's take my solution that I got for the 10 a.m. power flow equations, use that as the initial start for the 11 a.m. solution, for the 11 a.m. power flow equation. Right? The load doesn't change drastically in 1 hour, maybe fairly similar. So maybe the last solution is a good guess. Right? It's a good guess for the next one. And this example shows you that may not be the case. You can deviate a little bit. Depending on how nonlinear the function is, you may go to a completely different region of the system, right? Of the sort of solution space. And that's not ideal, right? That's not ideal. Okay. So if you look at this kind of behavior, so why does this kind of behavior happen? So mathematically, can you think of an explanation, right? So so this is sort of a numerical example, right? I can give you an example where you start close to a solution that you don't get to it. But mathematically, what in this update, suggests that you can have this kind of sort of wild, oscillatory behavior. Right? If you look at this update, what's not so good about this update? Or I guess sometimes what's good about this update, but what, mathematically in this update, what things will give you pause if you look at this, how you're solving the optimization problem? You're solving the equations. Okay, so this update involves a division, right? I'm dividing something by some other thing. So when you divide things, what do you worry about? Right? Dividing by 0. Okay, whenever your algorithm involves division, or multiplying by inverse of a matrix, you really start to worry. What if the thing I'm dividing is close to 0? Right? So then that's basically you take a very large step. It's roughly 0. Right? So that basically is what happened in this picture. The point you started at a relatively flat point of the curve. It's relatively flat. So your derivative is close to 0. Because you're dividing by the derivative, you're basically creating a very large number when dividing by 0, and you start to take a huge step. Okay? So this one step can get you very far away. And this one step can be, very far away from the desired solution or from your starting point, things like this. Okay, and then you have this, or then you sort of don't know where you end up. Okay, so this is one thing, one drawback has, right? Because you're dividing by a number that could potentially be 0. Okay, so there's nothing that says f prime of x cannot be 0. It may indeed be a very small number. Right? So sometimes it's hard to tell in practice whether, beforehand, whether the 0 will be small or large. Right? So this is one thing that, leads you to this sort of large jumps in the algorithm, right? So it's sort of jump from one region to another region. Okay? So this is one example we have. Right? So so convergence to so in chat. The people adding a check for when implementing the code, yes, so there's a check. You always check so-called condition number of this, right? So in the future, we're dealing with matrices. So whether a matrix is close to 0, close to 0, quote unquote, is something called a condition number. This you will check. But the bad thing is you can check, right? If it's close to 0, what do you do at that point? Well, sometimes you start with a new starting point, but sometimes maybe taking a large step is the correct thing. But often that's why it's tricky. So there's a lot of sort of there's a lot of engineering of the code. Right? Sometimes not so clear cut and dry what you do in the code. But this is definitely something you check. Right? You check in your code whether you're very careful whenever you're multiplying or a very large number or dividing a very small number. There's always something to be careful about whenever you write code. Otherwise, something will blow up. Right? So this is one thing. This is one bad thing that can happen. But what is another bad thing that can happen? Right, so one bad thing, there's multiple solutions, you get to the wrong solution. Right, sometimes the other bad thing, there is a solution, you just don't get to it. Okay, so for this curve, for example, you can start at the point, and you basically just oscillate. You never converge to anything. So if you look at, again, the update, there's nothing that says the update has to converge. So often you oscillate. Okay? You start at one point, just keep oscillating. And basically the way to solve this is you try a new starting point. Okay? You try a new starting point. Right, so this is something we can do, but the oscillatory behavior makes another thing difficult for us. Okay, because what happens when there's no solution? Right, so this blue curve never crosses 0. But there's nothing, again, nothing in the algorithm that detects this. Right? You can still run the algorithm. Right? The algorithm, you can still do the update. So basically, if this happens, if there's no solution, you oscillate. But when sometimes there is a solution, you still oscillate. So it's not clear, from the behavior of the algorithm whether there's no solution or there is a solution. You just happen to pick a bad starting point. Okay. So Newton-Raphson basically comes down to this, right? So it's a easy algorithm to implement. Okay, to write down. If it works, will work pretty well. If it converges, will converge pretty quick. Okay, so it has a good convergence property whenever it converges. Whenever it doesn't converge, then who knows what happens. When it doesn't converge, we sort of don't know what will happen. Okay. So, but for now, we need to one is to understand the equation. Another is to, recognize the fact that if sometimes this algorithm doesn't work. Sometimes the algorithm doesn't work. Any questions about the single variable Newton-Raphson before I go to more than one variable?
Can you make a negative guess for?
Yeah, you can make a negative guess. Right? So the function value may be very close to there. For example, you're solving the power flow. The angles are there. This could be negative. Right? So you can. None of this requires anything to be positive. None of this requires that. Okay, so when we go to more than one variable, things don't change very much. Okay, it's basically the same procedure. It's just that this. So obviously you can talk about the derivative, right? We don't have the idea of derivative anymore. This goes to the partial derivatives. Okay, so this is something called a Jacobian matrix. Okay, so we replace the derivative by a matrix because I have more than one variable. So then the procedure actually goes the same as before. Okay, so let's do it for two variables. Let's do it for two variables today. The next class we'll do it for more general n variable. But the idea is still similar. So for two variables, so let's say we're solving something like fx. Y equals to 0, gxy equals to 0. Okay, we want to find x and y that simultaneously satisfy these equations. All right, so the procedure is all the same. You basically still do Taylor expansion. Okay, still do Taylor expansion. So we're gonna assume the Taylor expansion exists for all the functions we look at. Okay? And turns out for power flow equations, they exist. It's a continuous, bounded, all this sort of equations. So Taylor expansion always exists for us. xy is some starting point I have. So if I have two variables, what happens to the Taylor expansion? What is the next term in the Taylor expansion? Anybody remember? Multivariate Taylor expansion. So there's always a constant. How do I write the derivative? Nobody remembers from Taylor expansion, right? So you have two variables, right? You have two variables. So the first is the partial with respect to x. Right? As you take a partial derivative with respect to x minus x0. Okay, so that's your first term with respect to x. Then you take a partial with respect to y. Right? So you have two things that can change, x and y. So we take a partial with respect to x and y plus the higher order terms. Okay, so this is our Taylor expansion. That's our Taylor expansion for the two variable case. Okay, for generally n variable case, you have n terms, right? Where you take a partial derivative on each of the, right? For each variable, you have a partial derivative. So g very similar. That y, partial g, partial y minus y0 plus higher order terms. Okay, so we're going to remove the higher order terms, right? We're not going to care about higher order terms. So we're going to neglect the higher order terms. So we're going to forget the higher order terms, and we're going to let delta x and delta y equals x minus x0, y minus y0 for sort of shorthand forms. Okay, so then the equation becomes f of xy x0, y0 delta x plus f delta y, right? So by in our shorthand form, g, similarly g dx delta x plus partial derivative of g dy delta y. Okay, so this gives us a linear system equations, right? This gives us linear system equations. And what we want is we want to solve, instead of solving f and g equal to 0, we want to basically solve these equations, solve this linearized equation to be equal to 0. So for this two variable case, we collect terms, we'll have f okay, so we solve this linear approximation with respect to it. Okay, we solve this linear approximation, right? So this is what we can do. We can collect these into a matrix form, right? Again, we're going to assume that we can solve system of linear equations. So collecting them into a matrix form, evaluate x0, y0, delta x, delta y equals to f of x0, y0, g of x0, y0. Okay, so this is just collecting them into a linear system. Okay, so any questions up to this point? Okay, so all this is sort of algebra, basically, just a simple algebra. Then if you look at this again, so we're seeing this matrix a lot, right? So instead of writing this thing out every time, we'll give this a name. I'll give this x0, y0. Call this a Jacobian matrix. Okay, so this is a common, this is a very common matrix you see in multivariate right? In calculus. Okay, so this is a Jacobian matrix. Evaluate at some starting point. Okay. Then the process becomes simple, right? We're going to solve j x0, y0, multiply delta x, delta y, to minus f x0, y0, g x0, y0. Okay. So we're going to assume this can be solved for delta x, delta y. Okay, so for example, you can think of delta x, delta y with j inverse minus j inverse of, okay, so you can think of this way. So again, in practice, when the system is large, we're never going to take the inverse. So we never explicitly take the inverse. But in this case, because things are Just for a notation wise, what we can think of, we take the inverse and multiply by. Okay. Then the process is easy. X1, Y1 equals to X0, Y0 plus delta X, delta Y. Right? So this is our correction term. Or you want to write this out, xk plus 1, yk plus 1 equals to xk, yk minus jxk, yk inverse multiplied by f of xk, yk, g of xk. Okay, so this is our steps. Right, so it's exactly the same as a scalar case. Okay, so you do a Taylor expansion of the function, approximate using linear functions, and then just keep approximating. Right, from the linear function, solve the linear system equations, do another approximation, and so on. Right, so this has the same property as a scalar one. If it converges, it converges quite quickly, actually. Converges quite quickly. But then you still have an issue of whether you have a bad starting point, or your J becomes close to be singular. Right? What happens when J is close to singular? What happens to your inverse, for example? So these sort of numerical issues do all come up. But the basic algorithm for solving the nonlinear system equations is basically this update. You compute the Jacobian, you solve a linear system based on the Jacobian, and you keep going, and you hope it converges. You hope this thing converges. So of course, for a power system, there's this, J is called the power system Jacobian or power flow Jacobian. And you look at the solvers people use, it's basically all a variation on this Newton-Raphson algorithm. Right, any questions on this two variable thing? Okay, so should we do the example? Yeah, the example quite long, so we won't finish today. Okay, so let's stop here. So the idea to stop here today. The basic idea is when you look at a nonlinear system equations, always think of converting it to a linear system. That's basically what this Newton-Raphson, this is called a Newton-Raphson update does. And even though it has some drawbacks as sensitive on the initial point, may not converge and so on, this does form a lot of the basics of more advanced algorithms. So it's used all over the place, used quite often. All right, so yeah, so if there's no questions, we'll stop here today. I can answer a question about homework or other things. If not, I'll see you next Monday. So since we have the midterm next week, take home Wednesday to Thursday, so there won't be a homework this week, right? So you hand in the homework for tonight, and then there'll be no homework for next week since we have a midterm. All right, okay, yeah, thanks guys. So I'll see you next Monday.